Recording in progress.
Hello, my name is Ayush Sinha and I am here to present my project work on the study of Andreev molecules in Josephson junction. Yeah, the outline of my presentation will be like this. Firstly, I'll tell you about the motivation behind the project, why we are doing this work, and then I'll let you know about the hypothesis, which basically comprises of the Andreev molecules and something about Josephson junction. And then I'll tell you about the methods that I've used in this work for the realization of this project, and in the end I'll tell you about the work that can happen and can be done in the future, extrapolating the work of this project. So the motivation for this is quantum computers. What is a quantum computer? It's basically a type of basically quantum computing is a type of computation that uses the collective properties of quantum states, such as superposition, interference, and entanglement to perform calculations. And the devices that perform quantum computations are known as quantum computers. But the age-old question remains as to how to create a quantum computer. So there are various proposed strategies of quantum computing like nuclear magnetic resonance, linear optical quantum computing, and superconductors. So as you can see from these figures, the top figure is based on the light propagation along beam splitters and mirrors and utilizing this for quantum computing. This is the standard procedure for linear optical quantum computing. And this figure below is based on superconductive quantum computing, which we are going to propose. A similar idea, which we are going to propose based on Andreev molecules and Josephson junction. So let's talk about the hypothesis now. So here's our setup. The setup is very simple. The colored objects are superconductors and the gray objects are insulators. So we have SIS Josephson junctions: superconductor, insulator, superconductor, insulator, superconductor, Josephson junction. So this superconductor is like SNS or SIS. We are considering co-joint version of a Josephson junction, which is SIS. So the superconducting phase, the current flows from left to right, as you can see, and the superconducting phase difference between the center and the left one is delta L, and the right and the center is delta R, and the superconductive coherence length is approximately equal to the length of the central superconductor L. So the Andreev molecules will be developed within the junctions of these superconductors, and we will accordingly to study the tunability of these Andreev molecules with respect to the phase factors so that we can perform quantum computation using these. So as I said, Andreev molecules in a Josephson junction is the qubit that we are proposing. Basically, we'll tune its energy levels, and this will be based on theoretical models, but we are proposing an experimental setup through which we can tune its energies based on physical factors. So now let's understand the method. So here, the Hamiltonian uses the standard Bogoliubov degenerate superconducting Hamiltonian. So H0 is the free Hamiltonian, and HWL is the so-called tunneling potential in between the superconductors, and delta X is the superconducting gap. As you can see from the right hand side here, delta X is a piecewise function in which for the left part of the superconductor, it has a phase difference of delta L, as I mentioned earlier in the previous slide. And on the right hand side, it is a delta R, and at the center it's 0. So we are keeping the center as the bottom line for this phase. So our ultimate goal will be diagonalizing this Hamiltonian. This is the theoretical model for our setup. So we have, as you can see here, we have two Dirac delta potentials, which is HWL in this figure, and H naught is the free Hamiltonian, which is just the kinetic energy plus the background potential. And 1, 2, and 3 regions have potential delta X, which is the function that we described earlier in this slide. And this is a schematic perfectly describing our system. And this defines the delta potential well, double Dirac delta potential well. So now we'll try to understand our results of the simulations. So this is basically energy in the units of delta, and this is the phase, the x-axis. So this is basically a non-local phase, implying that we will tune the phase on the right. We'll change the phase on the of the right to tune the Andreev molecule energy on the left. So when the effective length is basically length upon the coherence length. If the effective length is greater than 1, then we have the simplified figure, which is this on the left hand side, in which the there is no there's no mixing of the bands. These are the energy bands for the Andreev molecules, and when it's large enough, there is no mixing as expected because of the high coherence, because the coherence length is really small as compared to the lengths of the central superconductor. But however, when it's comparable, as you can see on the right hand side, if it's comparable, there's mixing of these bands and we get this kind of a figure. And this figure is theoretical. While experimentally, I'm not sure how they're done, but this is how you can tune the energy levels using the phase factors of the superconductors. And similarly, um, we will now study the variation of energy with respect to the coherence length, with respect to the effective length. So effective length is basically the length of the superconductor, the length scale of the superconductor upon the coherence length. And the variation of energy vary for different phases, as it can be seen in different figures. So we have this fixed delta R and we have plotted for various values of delta L. As you can see, there is a small dip and then there is steady rise, which goes to saturation value as the effective length increases. This implies that as effective length increases, the effect of phase on the energy level reduces. Is it basically it is removed, almost removed, because of because there's a competition between the length scales. The crossover is when L is equivalent to the coherence length, as I stated earlier. So energy can go up to the band gap maximum 0 to delta L. So I have not described this earlier, but we are only considering bound states, not continuous scattering states. We are only considering Andreev bound states in this work. So now we will come to the major effect of this work, which is the 2-pi periodicity plot with respect to the phase, which is non-local. So this is, as you can see here, this is a 2-pi periodic plot where L is very much larger than the coherence length, as you can see from the dotted figure, this one. It's 2-pi periodic as expected in Josephson effect, which is I is equal to IC sine theta. IC sine theta. And when L is comparable to the coherence length, you can see that due to the mixing of Andreev molecules, there is deformation in the current versus phase graph. And this deformation is as I said, due to the mixing of hybridization of Andreev molecules. So Andreev molecules just hybridize like hydrogen atoms in a molecule. So this is an analogous example you can think of as an analogous to hydrogen molecule. And we have fixed the right side phase to 3 pi by 5. This is just a value for neat plots. It's not there is no any physical significance of these value 3 pi by 5. So now we will understand what further work we can do. Further work we can do is what we can do is in the realm of topology. We can just replace the superconductor with topological superconductors. If we do so, then there will be Marana modes, and using these Marana modes, we can uh, uh, grade them into quantum computers. And the advantage of these Marana mode is that they're robust. But there's one problem with every quantum computer is that there is they decohere with respect to environmental factors. There's a lot of noise, and this decoherence will be reduced as a result of this topological effects which are introduced in the picture. So these are very nice pictures of braiding. You can see a braiding of topological qubits. The second picture related to the Marana modes and how they are non-local in nature. And the third picture is basically um, non-fractional Josephson effect, which is 4 pi periodic, as opposed to the 2 pi periodic graph, as I showed earlier. And this B part, this last graph, is energy spectrum of Marana modes. So that was my slide. Thank you very much. That's all from my side.